Hi, good noon to all. The title of the presentation is Uncovering One of the Last Unknowns in the Steel Industry, that is slag carryover through FactSage simulations. We all know the importance of slag free tapping in the steel making operations towards production of clean steel. So, the topic of presentation actually covers the thermodynamic modeling using FactSage simulations and validation through water modeling experiments. Myself, Dr. Ashok Kamaraj, a faculty member at the Department of Material Science and Metallurgical Engineering. My research lab is Sustainable Metallurgy and Industrial Technologies at the Indian Institute of Technology, Hyderabad, which is located in the southern part of India. So, moving into the topic, we can see transfer operations are very important in the steel making. So, there are several places that transfer operations takes place. We can see transfer of liquid steel from BOF converter to ladle, also transfer of liquid steel from electric arc furnace to ladle, which is named as tapping process. This takes place at the primary steel making section. As soon as the crude steel is produced, and the tapping operation will be taking place to transfer the liquid metal from one vessel to the another vessel. Another transfer operation that takes place in the steel making process is during the continuous casting, where you can see the liquid steel will be transferred from ladle to tundish and then tundish to continuous casting mode. So the difference between these two different transfer operation is one is taking place at the early stage of steel making, and the another, that is a teaming, takes place at the later stage of steel making. So whereas in case of the teaming, a mere entrainment of slag is itself is very dangerous, because that is going to give you some exogenous inclusions in the steel products. However, in case of tapping, you can allow some to some extent slag carryover, because the slag that carrying over from converter to ladle will be at a high temperature, and it can helps in dissolving some fluxes, and it can cover the liquid steel so that it can prevent the reoxidation, whatnot. All these, so there are some advantages over that. However, the disadvantages is the BOF slag, that which is actually carrying over into the ladle, that has lot of excess oxygen that comes from reducible oxides like FeO, MnO, P2O5. So there is always a trade-off, that how much amount of slag carryover to be allowed, and as much as possible for several steel critical steel that demands slag-free tapping. So the our work primarily focused on the tapping process, that is transfer operation that involves the transfer of liquid steel from converter to this ladle. We know that crude steel is produced and it is a BOF slag, and during tapping, generally there is a practice that the deoxidizers are added, aluminum, silicon, manganese, and some amount of slag formers are also added, like calcium aluminate slag, some synthetic slag of different compositions, like that. So as soon as the tapping is going to over at the end of the tapping process, this is because of a gravity dependent thing, the vortex formation will take place. And this vortex formation, once it is incepted, the upper phase, that is a slag, which will be carried over into the stream that is going into ladle. So this process is basically called as slag carryover. There is a difficulty in separation because it is highly gravity dependent, and the drain vortices, which is beyond the control of any operators, that there are a lot of reasons why the drain vortices forms. So these all these things put that slag carryover is one of the complex phenomena in the steel making process, and which requires a very precise control to ensure the quality of the steel. There are control methods available. We can see here that is a dart, which is a device that is placed at the top of right above the tap hole, and which has the specific gravity between the slag and liquid steel that expected to occupy the interface, so that the drain vortices can be destabilized. And there are IR cameras, as shown in the slide. You can see this is an IR camera, where this will be focused towards the stream, and the thermal imaging will be continuously obtained. And once the slag is entrained, you can see that the thermal images, the signal will be different, so that operator can take action by tilting back the BOF converter. These all how the today's practice that is happening in the steel industry for control of the slag carryover. So, given this background, we will be moving into the problem definition that is it is defined here. You can see the slag carryover during the tapping process. The slag carryover takes place. That is one of the phenomena that is very much of interest here. Through vortex formation, the slag carryover takes place, and as soon as the liquid steel stream is exposed to the atmosphere, you can see that stream will be attached to a hot air film, and atmospheric air will be entrained through this stream, and there is an oxygen and the nitrogen transfer into the liquid still from atmosphere. This is the second phenomena that is taking place when the stream is exposed to atmosphere. The first phenomena here is a carryover of an oxidizing slag, and the second phenomena here is basically the entrainment of air and diffusion of oxygen and nitrogen through this boundary layer. And finally, what happens, you can see that is the steel liquid steel can be cylindrical, or it can broken into multiple droplets, and the surface area increases, and it can basically encourage more. So as such, if you see this process, there is a lot of excess oxygen is basically going into ladle. Oxygen inputs, one is through slag carryover, and another is through atmospheric interaction, and another is there are some dissolved oxygen always present in the crude steel. So these are all the amount of excess oxygen which is going to cost your deoxidizer in the later stages, that all coming into the ladle through the during the tapping process. Okay, we have extensively studied and modeled this excess oxygen input through a thermodynamic model, mathematical model. That is a separate paper. One can refer to that to know how the excess oxygen input can be calculated. However, the present work, what I'm concentrated here and then presenting here, is the quantification of the slag carryover. As such, not only the excess oxygen, as a whole the slag carryover, we are quantifying through FactSage simulations. In order to do that, you need an extensive data that requires from the industry. By seeing the process of tapping, the input of this process, you can say the temperature is the initial temperature, tapping temperature, and the crude steel composition, BOF slag, how much weight is going, that is what going to be my unknown, which is what I am going to calculate through FactSage calculations. And the tapping additions, how much it is added in the every heat, deoxidizer, slime, synthetic slag, these all. Crude steel composition also, always it is not possible to get the weight percent oxygen. So we have computed in such a way, the program is given in such a way in the equilibrium calculations. Initially, we will also calculate the weight percent oxygen, and then we will go for estimation of slag carryover. So finally, the output of the process is the LF temperature. That is um, you can see once the tapping temperature and after the process, and once the ladle reaches to the ladle furnace, what is the temperature? That is the final temperature for our calculation in the equilibrium module. And the refined steel composition and the weight percent oxygen, including the weight percent oxygen, and the final slag composition weight. So this is basically an input. The list of inputs, if you give in a equilibrium model, these list of output basically comes out through the equilibrium module of the FactSage. And doing some exercise, one can calculate it's basically an equilibrium, and thermal and mass balance along with the chemical reactions. So one can perform this calculation and then estimate basically the slag carryover. I'll just explain in the next slide how that has been done. So, as I told, equilibrium module is what used. That is basically the heart of this calculation. Begin with you have to go from the this green box first. You start the simulation process. You give the input of steel composition, slag composition, and the tapping temperature, and get into the equilibrium module, and the output is calculated. Equilibrated steel and slag composition at tapping temperature. This equilibration is here essential because to estimate the weight percent oxygen, exactly what it is present in the liquid steel, because that is most of the time unknown in the steel industry. For all the inputs, what generally they may know is what is the final carbon content. So given this carbon content, equilibrating the liquid steel, that is a crude steel, with the slag composition, and estimate what is the weight percent oxygen present in it. Now this output crude steel is recycled you can see, then you change it to per ton of crude steel, and the BOF slag, which we do not know, right? During the tapping process, how much of the BOF slag is done, that we do not know. So you keep that as an unknown. We know that the close bracket with the A, that we put it as a variable, and then deoxidizers whatever added in the tapping process, like silicon and manganese, all these things can be given as an input again into the equilibrium module. If you calculate, basically this will give an liquid steel with x kilogram and the slag with the y kilogram at the final temperature of mm, LF temperature. Initially, the process is starting with the tapping temperature, and the equilibrium calculations are subjected to LF temperature, because in the industry I know at the tapping what is my composition, and at the LF what is my composition. Now I have to do the equilibrium calculations with the unknown, and now the process involves in the industry where we collected data. Basically, it is a silicon killing in the deoxidation process. So the amount of silicon that is present in the crude steel minus, the crude steel present in the initial, right? When that silicon difference is 0.001, basically we can say the equilibrium calculation is perfect and meeting the composition of the industry. Then you can go and calculate what is the exact y exact y that is a slag carry over, how much amount it is, and with the lime plus a synthetic slag, along with the synthetic slag, that can be recorded, right? Then if the silicon condition is not met, then basically we have to go again to the equilibrium model, add the BOF slag what is given A into 0.05 kilogram. So in this way you can increment the small amount of BOF slag every time, so that you get an exact amount of BOF slag. When you basically add, you are involved in calculating the slag carryover, what exactly has gone, based on the recovery of the silicon that is added as a deoxidizer, right? So this is what the calculation scheme that we adopted for estimation of FactSage, estimation of slag carryover using the FactSage equilibrium model. So given this, we will be able to estimate not only the slag carryover amount, we also will get a lot of insights about the process, like the evolution of the slag composition, evolution of the steel composition, and all these things. And basically I'm going to discuss about influence of these parameters on the slag carryover. So the results are given here. Close to some 150 industry heat data we have taken, and then we computed through FactSage, and then we could able to calculate the slag carryover amount. You can see that varies from 0 to 6 kilogram per ton, and different grades are given here. With respect to different grades, we can see some grades are always lower, and some grades are it actually increases, and the grades are arranged in such a way that the slag carryover increases from 2 kilogram per ton to 6 kilogram per ton. But interestingly, if you note down these grades, which basically talks about as you move from left to right in this direction, the end carbon and the end phosphorus are less when you are moving from this left side to right side. It means if the BOF practice that involves maximum to carbon and phosphorus to be removed, then basically you are ending up with more slag carryover. Here there are some intentions given with weight percent carbon and weight percent phosphorus. These are all some obvious conclusions that we got from the results. And the slag carryover predicted has been compared with an empirical relation with the FactSage estimated slag carryover with the coefficients given here, and you can see till 5 kilogram per ton the prediction success is somewhat okay. However, beyond 5 kilogram per ton the prediction success is very poor. And this is the slag path, how it is actually traveled. You can see this is the BOF slag composition regime, A1 and A2. A1 is completely liquid and A2 is liquid slag plus some saturated MgO. And when basically the deoxidizers are added, the BOF slag moves to this regime of liquid slag plus dicalcium silicate, or regime B, where the liquid slag is there. And upon the flux additions, this B and C regime compositions are moving to a final composition of D and AF. This is how the slag path that travels in case of tapping process. And you can see the slag carryover when is very much sensitive to certain parameter that we have analyzed. The one of the parameter is the temperature difference between tapping and the LF process. You can see the conditions for the zone A1 slag carryover when it is going to be greater than 5 kilogram per ton. This is the region where it is for less than 5 kilogram per ton, that is less than 80 degree, and greater than 120 degree, it is going to be have a higher slag carryover. This temperature can be indirectly connected to the interfacial tension. We all know that this interfacial tension plays a major role in bringing the vortex formation. And the another inference from slag carryover, what we have plotted for all the heats with the sulfur to carbon ratio, because the sulfur and carbon or interstitial elements that are present in the liquid steel, which can also bring some changes to the interfacial tension. And the conditions established here for the zone A2 slag carryover BOF slag for the less than 5 kilogram per ton, the ratio need to be 0.95. Okay, so primarily what is the observation comes out from here is the interfacial tension that involved can be controlled by several parameters. More importantly, temperature and the impurities present in the liquid steel, which has a major influence on the slag carryover. Importance of excess oxygen in the slag carrier estimation, I think I need not to emphasize to this audience, because all of us must be very much aware about it. We want clean steel, and where it has to be a slag free tapping. So based on these investigations, we propose a certain control measures for slag carryover, tapping temperature control, optimize the distribution in the desulphurization between external and the LF desulphurization to control the excess oxygen input, and some catch carbon practice can be followed. BOF slag engineering can be done, and we wanted to validate this. So the water model experiments are planned. The schematic pictures of those models are given here, and the results are validated here. You can see that this is the BOF slag regime. That the carryover ratio, it is nothing but a kilogram per ton, and this is the BOF regime. And you can see as the kinematic viscosity increases, basically your slag carryover decreases. And another inference from here, when we plot it with the interfacial tension, it is very clear that as the interfacial tension increases, the slag carryover decreases. These all are in very much in agreement with the FactSage results, and we went forward for industry trials to make it. You can see there is the phosphorus reversion is one of the indices for the slag carryover, which is very random before adopting our change in practice. And the change in practice, what we did is addition of line towards slag engineering with respect to the tapping temperature. If the tapping temperature is increases, the amount of lime added is also increases, and addition of lime basically decreases the viscosity of the slag. And altogether, for a 1 month of trial, we could see the phosphorus reversion is in very much in control. You can see always it is less than 100 ppm. I can say till date this is getting 100 ppm less than phosphorus in the crude steel is a challenging task. But we could able to get consistently less than 100 ppm for all the grades after we adopting this practice of slag engineering to control the slag carryover. So the learning is increasing the temperature and the basicity basically decreases the viscosity of the BOF slag. That increases the interfacial tension, and hence the slag carryover decreases. So I would like to conclude here. We have conducted very systematically using the FactSage simulation to understand the slag carryover process. And we understand that based on the FactSage investigation, the slag carryover is actually influenced by interfacial tensions of the liquid steel and the slag, and water model experiments have also confirmed the same thing. And based on all these understandings, we went to the industry trials to confirm that there is a strategy to control the slag carryover by slag engineering. I would like to give the list of publications that we have done in this area. There are very detailed investigations we have done using the thermodynamic modeling, water modeling, and role of slag carryover on the non-metallic inclusions in the electrical steel. If anyone of you interested, please go through it. And thank you all. And once again, I thank the organizers for providing this wonderful opportunity to present our work on slag carryover using FactSage simulations. Thank you.